So our next talk is going to be Caleb Fassett talking about dating key lunar events with Artemis, and he's presenting for Barb Cohen and a bunch of other folks that you can see on the screen. So Caleb, are you there?
I am. Quick mic check.
Great. Yep, we can hear
Great.
you. It's all yours.
Wonderful. Okay, so thanks for having me. I wanted to point out that Barbara Cohen was the one who put together the abstract and did the cat herding for the original work here. And obviously, there's a lot of people in this virtual room who've thought very hard about this problem for a very long time. So I hope everybody speaks up in the discussion and the breakouts if I say anything people disagree with. Next slide, please. So for the purposes of doing geology on another planet, geochronology is of the utmost importance. And you can look to a huge number of community-produced documents to make this point. But the reason for its importance and why we care about this problem is basically because geology requires knowing something about the temporal dimension of things. So on the moon, getting geochronologic information is really critical for understanding both the moon's evolution, like the history of volcanism, and other processes that are planet-wide, but also broader solar system evolution, because the moon is such a touchstone for the chronology information we have in the inner solar system. It's also important for the timing of specific events, and also something I think is really important that sometimes gets lost is the rate of processes that occur. So you need chronology information to understand the rate at which the moon is changing and evolving. So Artemis has the potential to really push forward all these elements. So if you go to the next slide, please. You've all seen this diagram in one of its forms at some time or the other many, many times. But one thing to think about here is that until we had samples from Apollo, we didn't actually have the connection between how old surfaces on the moon are and their age at all right. So people had predicted the ages, and they were off by an order of magnitude. And so gathering samples was really critical for this problem. But even with the Apollo samples, there's a few things I'd like to point out about this curve, which are probably pretty well known, but are worth remembering, which is that there's really this big gap before 3.9 billion years old with Imbrium. And there's also a big gap after 3 billion years old, mostly because there's not a ton of lunar terrain that has that epoch. And to be on this chart, I want to point out that you really need to have both a sample area and also a sample that you can tie to that area. So there are chronologic measurements that fall at less than 3 billion years, but most of those, you don't really know where they came from. And so you could do really important and critical science with that kind of information, but it takes a special point to end up on this plot. So next slide, please. In the South Polar region, we've already heard some of this information. We'll hear some more in a little bit, but there are a few specific craters and basins we can hope to date. I'll skip SPA since I know it's going to be talked about in detail in a second, but a couple of the younger large impact events that we could hope to date are Schrödinger, which we've seen on earlier slides, and Shackleton. And in both instances, there are what I would call reasonable crater size frequency distribution measurements that would allow you to add these points to that plot where we have relatively little chronologic information for the moon. I'd really like to double the number of points that we have tying this impact crater chronology to absolute ages, because it's so important. So both Schrödinger and Shackleton, I think if you sampled in the South Polar region in the right places, you would stand a very strong chance of being able to get their ages. And this idea that you could get Tycho that Brett pointed out earlier is also extremely exciting. I hadn't realized that, and I think that's really impressive. Next slide, please. The other thing that is I think is more in terms of process ages that we really want to know with the geochronologic perspective is the age of the PSRs. And the reason we'd like to know this is in part because it'll speak to the provenance of the volatiles within PSRs. Ariel Deutsch recently published a paper that I think is really great that pointed out that the very youngest fresh craters seem to have an absence potentially of volatile deposits, and it might be an indicator, at least tentatively, that volatiles are not from this Copernican era. And so getting an absolute age samples of that might allow us to nail that down would be really important. And we've already talked in Brett's really nice presentation about how the regolith evolution at the South Pole might differ geochronologically as well. Because there's other data that suggests this, including things like grain size, which might differ at the South Polar high latitudes than at the equatorial region. Next slide, please. The final thing I wanted to just point out is something that I know Barbara would emphasize, which is that shouldn't just be an astronaut-driven program. We really want to think about both the incredible value that we can get from what astronauts do, but also the potential synergisms that exist with robotic and in situ measurements. So there are reasons we still want to consider robotic sample return and also in situ geochronology in places where we might not send astronauts. So as part of Artemis, and as we try to get increased geochronologic information for the moon, we really should do this as well. So I'll stop there, saying that I've run my 5 minutes out. Thanks.